Okay, good morning. There's a new exercise sheet which is distributed, and there are a few more copies here if you need more. And I was asked to again announce that please, if you worked on your exercise sheet alone, it would be nice if you could try to find another one who's also working on exercise sheets alone and try to form a group of two, because otherwise there are lots of sheets to grade, and the poor students who have to do that, they have a lot to do. So it would be better if you solve exercise sheets in groups of two. So please solve the exercise. And if you work together, then please don't produce two separate copies with identical solutions but different names. Instead, just give one copy with both names on it. Otherwise, we have to grade it twice, and it would be nicer just to grade it once. So please solve the exercises in groups of two, and then only hand in one exercise sheet. And then several people who study mathematics and have computer science minor ask me about regulations concerning examinations. And maybe the best thing is if those people who study mathematics could come to me after this lecture, and then I can answer all their questions. So please, all mathematicians, if you come to me after the course, that would be a good idea. Okay, so what did we do in the last lecture? We looked at declarations, we looked at expressions, and we looked at patterns. So these are the three of the four major components of Haskell. So we had declarations, we had expressions, and we had patterns. And now the only thing that is still missing to finish our explanation of the Haskell syntax are types. And so, let's see, maybe this is better. And so today we will introduce types in Haskell. So how do types look like? Well, so types is what we are going to deal with today. And this is the next chapter. So this is chapter 114, the last chapter on the basics of Haskell. And after today's lecture, we will look at certain specific features that we already have introduced, but then we will look at certain programming techniques, how you can exploit those features that Haskell has in order to write particularly nice programs. Okay, types. Now, every expression has a type in Haskell, and a type is simply a collection of somehow similar values. And we have already seen many forms of types in the examples, but now we introduce the grammar, which shows how types are generated. So one possibility to introduce a new type is the following. Types are built using so-called type constructors. So this would be done like this. A type would look like this. We take a type constructor, and a type constructor takes a number of already existing types and produces a new type out of it. So type 1 to type n are types, and if you apply this type constructor to these types, then you get a new type. And type constructors are written in Haskell by strings which start with a capital letter. So these are strings starting with a capital letter. And so unfortunately, they look like data constructors. Data constructors are also written as strings which start with a capital letter, but they are different. So examples for such type constructors that we already know are, for example, things like bool. So bool is a type constructor of arity 0. It is a type constructor which does not take any type. Normally you get some input types and you produce a new type out of it. But n can be 0. So bool does not need any input type. Bool is just a type on its own. It's a type constructor of arity 0. Another type constructor of arity 0 is int, or float, or character. So these are predefined type constructors which produce new types. They don't need any input type. So these are type constructors, predefined type constructors of arity 0. And we will soon see that you can define such type constructors yourself as well. But it's important to keep in mind that these are types. They make a new type out of existing types. These are not data objects. So they look like data constructors, but don't confuse them with data constructors. Data constructors construct data objects. Type constructors construct types. Data constructors are, for example, something like true or false. So they are also strings starting with a capital letter, but well, these are objects of this type, for example. Okay, now, as I said, these are predefined type constructors, and there are also predefined type constructors of higher arity than just 0. And we know, for example, one type constructor of arity 1. So this is a type constructor which takes a type and gives us a new type. The only special thing is that it's not written in this way, but it has a special notation. And the special notation are square brackets. So this is adding square brackets. This is a type constructor. It takes one type and it produces a new type. So this is a predefined type constructor of arity 1. So it's a unary type constructor. And so what happens is it takes a type and it produces a new type. So if you have the type int, then you can apply this type constructor and you get a new type. The only thing is we don't write first this and then int, but we write this into the square brackets. So this is a new type, and it is the type of lists of integers. Lists of elements of type int. Whenever type is a certain type, then type in square brackets is the type of lists where all the elements have the type of the type that is written between the square brackets. Now, obviously, you can also write something like this. So this thing here is a type. And if you apply this type constructor, which puts square brackets around it, you have a new type. And this is the type of lists of integers. So the elements of these lists are, again, lists. Now, this we have seen before. We also know a type constructor of arity 2, a binary type constructor. Do you have any idea how this type constructor might look like? So we had that before. If you have two types, how can you make a new type out of them? Well, for example, if you think of a function like square, what is the type of square? It's a function from int to int. So you take two types, int, and you make one new type out of it by writing an arrow between it. So the arrow is a type constructor of arity 2. So if type 1 and type 2 are types, then you get a new type by writing an arrow between it. So arrow is another predefined type constructor of arity 2. Of arity 2. And, well, the meaning is this is the type of functions which go from this type, type 1, to this type, type 2. So, for example, if we have something like this, this would be the type of functions which map lists of integers to an integer. So this would be the type of functions from list of integers to integers. And now, the last predefined type constructor that we also already know has arbitrary arity. So this last type constructor takes arbitrary many types and makes one new type out of it. And this is the constructor which simply puts round brackets around the input types. So you take the input types and you write round brackets around it. So it would look like this. You have n types, type 1 to type n. And if you write round brackets around them and separate them by commas, you have a new type, namely the type of tuples. So this type consists of tuples, n tuples, and the first component has type 1, and the second has type 2, and so on. So this is a type constructor of arbitrary arity, and examples would be something like tuples where the first component is an integer, the next one is a function from int to bool, and maybe the last one is a list of characters. So this is here you can see we have 3 input types, this one, and this one, and by putting them between round brackets and writing commas between them, we have a new type. This is the type of tuples with 3 components, where the first component is of type int, the second is a function from int to bool, and the last one is a list of characters. Now, these are all things that we had before. The most interesting one is the last. And the last one is this. So as a type, you can also use a variable. So this is a type variable. So whenever we need a type, we can also, instead of writing something like int or list of integers, we can also write a variable. And this variable stands for an arbitrary type. And now to explain what this is good for, we have to look at some examples. And this concept that we can realize by using these type variables is called polymorphism. And there are 2 forms of polymorphisms in programming languages. And Haskell has both forms of polymorphism, and I will try to explain both of these forms now. Now, the first form of polymorphism, which is the form where we need these type variables, is called parametric polymorphism. So this is needed for parametric polymorphism, and let me try to explain what this is first. So what is, in general, polymorphism comes from the word polymorphy. Polymorphy? Polymorphy? Okay. Anyway, it means that something can have different forms, and if you use it in this connection, it means you have functions which you can apply to arguments of different types. So it's not just like a function which goes from int to int. Such a function you can apply only to integers, and that's it. But we now look at functions which you can apply to arguments of different types. So in general, the idea is polymorphic functions are functions which you can apply to arguments of different types. So not just to integers, but probably to integers and to booleans, or to integers, to booleans, and to whatever, lists of characters. So polymorphic functions are functions which can be applied to arguments of different types and then there are 2 possibilities. One possibility is that no matter what arguments you apply the function to, the function always does the same. So you have just one single implementation of this function, and you use the same implementation no matter whether you apply to integers or you apply to booleans or you apply to characters. This is called parametric polymorphism. So parametric polymorphism means use the same implementation of the function for all types of arguments. no matter what types the arguments have, you always use the same implementation for all types of arguments. And the other form of polymorphism is called ad hoc polymorphism. And this means, depending on the types of the arguments, you use different implementations. So this function has many implementations, and in order to decide which of these implementations to use, you look at the types of the arguments. So if the arguments are integers, you use implementation 1. If the arguments are booleans, you use implementation 2. So there are different implementations of the same function and which implementation you use depends on the types of the arguments. So depending on the types of the arguments. And Haskell, now not every programming language has both forms of polymorphism. There are some languages which have no polymorphism at all. Haskell has both of these forms. For example, Java. So if you heard the introductory lecture on Java, then I or Professor Bischoff said Java has just ad hoc polymorphism. Now this is not true anymore because there's a new version of Java which was heavily influenced by Haskell. So the main designers of Haskell have worked together with Sun to improve Java. So the new version of Java has many features that you now find in Haskell. So the new version of Java has both of these forms of polymorphism as well, but this is very recent. So this means what you learn here is interesting not only if you want to do functional programming, but also if you want to work with modern imperative or object-oriented languages. Okay. This, by the way, also shows that functional programming is interesting because this influences also imperative and object-oriented languages. Okay, so we have both of these forms of polymorphism. Let's start with parametric polymorphism, which is the form of polymorphism which is usually not found in imperative languages, but as I said, this is now going to change. And the idea of parametric polymorphism is you have type variables. So instead of saying a function is a function from integers to integers, in these types you can also use variables. And here is an example. These are two examples for parametric polymorphism. They would look like this. So an example for parametric polymorphism are the functions it and len. And here the idea is we use type variables in the type declarations. Use type variables in declarations. So what you can see is that it is a function from type A to type A. So the type of it is A, arrow A, and A is a variable. So again, variables are written with by strings which start with a lowercase symbol, but this is meant to be a type variable, not a variable for data objects. They look the same. So this A stands for a type, and this means you can apply this it function to an object of an arbitrary type. So then you would substitute A by int, say. And if you apply it to an integer, then the outcome will also be an integer, because here we have the same A. If you apply it to a Boolean, then the outcome will also be a Boolean, because here is the same A. And what does it do? Well, it is the identity function, so it just returns the argument. So it of 5 will be 5, but it of true will be true. And both of this is completely legal. So we have a type variable, and the type variable may be instantiated by any type. So indeed, you can apply it of 5, which will give you 5, but you can just as well say it of true, which will give you true. So This you can do with it, and it works in the same way with length. So the length function that we have here is again meant to compute the length of a list, and it can compute the length of a list with arbitrary elements. So you can apply this length function to lists of integers, but also to lists of booleans, or list of characters, or lists of whatever. The outcome will always be an integer. And you can see you use the same implementation of len no matter whether you regard lists of integers or lists of booleans, because in order to compute the length of a list, it doesn't really matter how the elements look like. You just, well, check how long this list is, and you don't need to know anything about x or x's here, just the length is interesting. So the same implementation can be used no matter whether a is instantiated by int, or a is instantiated by bool, or a is instantiated by functions from int to int, or whatever. So you can, with this len function, you can compute the length of the list 1, 2, which would be 2. But you can also compute the length of the list, hello, which would be 1, 2, 3, 4, 5. So here a would be instantiated with int, here a would be instantiated with character. Now, one more example to show how this works with these type variables. This is an example for the predefined function append. So we had the append function already in the last lecture, but there I presented a version which could only append 2 lists of integers. Now, that's of course a completely unnecessary restriction. You can just as well write a function which appends 2 lists, and the types of the elements can be anything. So it can be integers, but it can also be booleans. The outcome will be a list where the elements have the same type as the elements of the input lists. And it would work as usual. So this ++ operator is predefined in Haskell. So this definition you can find in the prelude of Haskell, of your Haskell interpreter or compiler. And there this ++ function is predefined. And it's defined like this. If you append the empty list to a list y of y's, you get y's. And if you append a non-empty list which starts with x to a list of y's, you get a list which starts with x, and then you get a recursive call where x is appended to y's. And you can apply this to lists of any type, but it's important, it makes a difference whether you write many a's or whether you write a, b, and c. Because all these variables have to be instantiated in the same way. So if you instantiate this first a by int, then also the other a's in this type declaration are instantiated by int. If it would be a function from lists of a's to lists of b's to lists of c's, then a, b, and c could be instantiated in a different way. So in general, how would that work? So in general, a function of the type 1, arrow type 2 can be applied to an expression of type. In general, you would expect that such a function you can only apply to expressions of this input type, type 1. Now, that's not true if you have parametric polymorphism. You can also apply it to expressions which have a slightly different type, so type underlined, provided that you can instantiate the variables in these types, so in this type and in this type, in such a way that they become equal. This concept is called unification. So if there is a substitution sigma of type variables, so the type variables in type 1 and in type underlined, of type variables such that if you substitute if you instantiate these type variables in this way, then type 1 will be the same as the type of the expression that you want to apply the function to. And the result of the application will then be not type 2, but sigma of type 2. So the result has the type sigma of type 2. So let's look at an example to illustrate this. So suppose we want to we look at the following expression. The list of true should be appended to the empty list. Now, what are the types? So the type of plus plus is, well, we have seen this in the type declaration. It takes a list of arbitrary elements of type A and another list, elements must have the same type, and it returns a list of elements of the same type. What is the type of this? Well, the type of this is list of Booleans. It's a list, and true has the type bool, so the type is list of type bool. And what is the type of this?
List of Booleans too.
Why? Why is it list of Booleans? If you just take the empty list, how do you know that this is a list of Booleans?
Because the function declaration is from list from 8 to list to 8, list to 8.
Right. So this is what will come out indeed in the end. So this must have the type list of Booleans, otherwise you may not apply this over here. But to determine this, if you just look at the empty list as it is, this has the type list of something, and you don't know what. So in general, this has the type list of B. B is a new type variable different from A, because this is a list of objects of arbitrary type. Now, in order to apply this function, we need to find a substitution, sigma, such that this thing and will be equal to list of Booleans, and this thing will be equal to list of B's. So we need to find a substitution sigma such that the first argument is the same as the type of the first argument required by this double plus, and the type of the second argument is the same as the type of the second argument of double plus. So this is a unification problem, and Haskell performs this unification. So this concept is called unification. We need a unifier. The sigma is called unifier. We need a unifier which makes these types equal. So this type and this type must be equal, and this type and this type must be equal. And okay, there's just one solution. Sigma has to do the following thing. It has to replace A by bool and B by bool. So indeed, as you said, this only works if you regard this as the empty list of Booleans. In general, this can be the empty list of anything, but here it must be the empty list of Booleans, otherwise this would not be type correct. And now you know what the outcome is. So the outcome has this type. The result has this type, but you have to apply the substitution. So in other words, the result also has the type sigma applied to list of A's. So the result also has the type list of Booleans. So this is how this type checking intuitively works with type variables. And you can perform this type checking automatically. Moreover, if you drop these type declarations, so in Haskell, it's good programming style to include these type declarations, but if you don't write them, then the compiler or interpreter computes them on its own. So you can compute this type declaration from these equations. So if you look at these equations, you can find out that plus plus must have this type. This is the most general type that plus plus can have. So plus plus could also have the type list of int to list of int to list of int, but also list of bool to list of bool to list of bool. And Haskell tries to compute the most general type from the equations if you don't give the type declaration. So if type declarations are missing, then Haskell computes the most general type of a function or of an expression. And how to do this, so how to check whether expressions are well typed or how to compute these types, this is something we will look at later in the lecture. So this will be chapter 4 of the lecture. When we speak about how to implement a language like Haskell, well, one part of the implementation is a type checker. We need to find out whether expressions are well typed. We need to find out what type an expression has. And this can be done automatically. And how this is going to be done, we will see later on. So this is the idea of type variables. Now, what we've seen up to now is we've seen that there are some predefined type constructors, some of arity 0, like bool, int, and so on. And you can construct new types by writing arrows or list brackets and so on. But this is still rather restrictive. You would also like to define completely new types. So types where you do not rely on predefined type constructors, but where you define new type constructors on your own. And I will show you how to do this in a minute. Okay, so now the next question is, how can we introduce new types and new type constructors? And there are two ways of doing this. So we want to declare new types and new type constructors, which make new types out of existing ones. Now, first of all, in contrast to all the other declarations that we had up to now, such type declarations where you really introduce new types are only possible on top level. So you remember that there are local declarations which you can write using the keyword where or the keyword let. These introductions of new types you can only write on top level. So only on top level, not in local declarations. And to deal with this, we have to modify our grammar a bit. So now a Haskell program is no longer a sequence of arbitrary declarations, but a sequence of top declarations. And every declaration is also a top declaration. So all the declarations that we had up to now, you can also write on top level. But there are some more declarations which you can write on top level, but nowhere else. So now a program is just a sequence of top declarations, top decal. And, well, decal are those declarations that we know up to now. So they are function declarations and pattern declarations and all this stuff. So all of this stuff you can also write on top level, but there are some more things you can write on top level, but not in local declarations. And the first possibility, what you can do is you can introduce new types using the keyword type. Not surprising. And this is the first variant how you can do this. So if you use the keyword type, then what you introduce by this is just an abbreviation for a type which you could also express otherwise. So this is called a type synonym, or Typabkürzung in German. So this only is an abbreviation for already existing types. So here are some examples. So what you do is, in such a type synonym declaration, you first write the keyword type, then you introduce a new type constructor. So you invent a new word, for example, a new type constructor position, and then you may write an equality sign, and now you describe how this type should look like, and you can say, okay, positions should be pairs of floating point numbers. So you could write something like this. And the meaning is the following. Now this is already a type that we know. Float is predefined, and this is the type of tuples of arity 2 where both components are floating points. So these are pairs of floating point numbers. And instead of having to write this, if you write many functions on pairs of floating point numbers, then as an abbreviation, instead of writing this, it might be nice to introduce a new word for it, and this just introduces this new word, position. So whenever you write position, instead of writing this, you can now also write position. It's just an abbreviation, nothing else. So now the type position is completely identical and equivalent to writing float. And position is a new user-defined new type constructor of arity 0. Now, one of these type synonyms is predefined in Haskell. So in Haskell, a type constructor string is predefined. And string is simply an abbreviation for a list of character. So this is completely the same thing. Whether you write string or whether you write list of characters makes no difference to Haskell. You can write whatever you want. This is just an abbreviation for this. This is predefined in Haskell. Now, these type constructors don't have to have arity 0. They can also have higher arity. For example, let's introduce a type constructor of arity 2. And what this type constructor should do is it should take two types and make a new type out of them by building the tuple of these two types. So let's call this type constructor pair. And if we want to have a type constructor of arity higher than 0, we have to add variables after this type constructor. As you can see in this grammar, we can add n variables, and then we have a type constructor of arity n. So this should be arity 2. It takes two types, a and b, and then produces a new type out of it. And the new type that we want here is pairs, where the first component has type A and the second has type B. So now pair is a new type constructor of arity 2. And as you can imagine, whether you write pair, float, that is identical to the type position. So this is an abbreviation for the type of pairs of floating point numbers, and this is also such an abbreviation. But pair is a type constructor of arity 2, so you can apply pair to two types, this type, and it is defined like this, so it gives you a new type of pairs of floating points. So, however, this is really just abbreviation. If you don't want to, you can always avoid using these type synonyms by simply writing the stuff that is on the right-hand side. So in these abbreviations, they are rather restricted. If you really want to introduce completely new data types, there is another way to do that, because here the restriction is this type constructor that you introduce here may not appear on right-hand sides. So type synonyms are not recursive. So in other words, the newly defined type constructor, so something like pair, may not appear on the right-hand side over here. The newly defined type constructor may not appear in the right-hand side of its definition. So here you really have to, this is just an abbreviation, and this type that is on the right-hand side already existed before. So this does not use any of these new introduced type synonyms. If you want to do something more interesting, there's a different way to do it, and this declaration starts not with the keyword type, but with the keyword data. So this is really the way to introduce new data structures. introduction of new data structures. And the grammar looks like this. So it begins almost in the same way. So after the keyword data, you introduce a new type constructor. So again, this is a new name that you invent. This type constructor can have arbitrary arity, and you have to add as many variables as the arity is. But now you give a list of new data constructors. So these are data constructors which construct data objects of this type. And there may be many of these data constructors, k data constructors, and you just list them after each other. Let's look at a first easy example. Here is the first easy example for the introduction of new data structures with this data construct. So you can do something like this. If you write this first declaration, then this means here we introduce a new type constructor color, which has arity 0 because there's no variable here. So color is simply a new data type. And then after the equality sign, you give a kind of EBNF-like grammar by showing how objects of type color are constructed. So in this case, the type color has simply 3 objects, and they are called red, yellow, and green. So red, yellow, and green are data constructors. They are used to construct the objects of the data type color. And in fact, these are all objects of the data type color. So what we do here is we basically describe how objects of the new data type are constructed. Of the new data type are constructed using a kind of context-free grammar in EBNF notation. So an EBNF-like context-free grammar. So this indeed is a context-free grammar which says color can be reduced to either red or yellow or green. So these are, in fact, the only words that are in this language. So color is either red or yellow or green. So these are very simple enumeration data types. And here you simply list all the data constructors of the respective data types. So the data declaration simply lists all data constructors of the respective data type, and they are separated by vertical bars of the new data type. And so in our example, color, and also the next example, my bool, are new zero array, so arity 0 type constructors, and the data constructors of color are red, yellow, and green. And in a similar way, you could define the data type bool. So since bool is already predefined, I defined my bool. And my bool is a new type constructor of arity 0, so it's a new type. And there are 2 data constructors, my true and my false. So these are the only objects of this data type. And, well, this is the way how you can define Booleans. And now, after introducing these data types, you can write algorithms which operate on them, for example, using pattern matching. And you remember how pattern matching works. As a pattern, you can use any type consisting of data constructors and variables. Now, these data constructors are very trivial. So if you want to write a strange function traffic light traffic light changes from red to green to yellow, and from yellow to red, you can write a function like this. And here we simply do pattern matching by using these type constructors, using these data constructors in the definition of the function. And in a similar way, you can write the und function, the Boolean conjunction function, on our own data type myBool. Here we do pattern matching with these patterns, which just have the data constructors like myTrue and variables. So this is the und function, but now with the data constructors of our own data structure and not the one of the predefined bool data structure. Now these data structures are very trivial because they are finite. They're just finitely many objects. Color has 3 objects, myBool has 2 objects. That's not very interesting. So more interesting data types have infinitely many objects. And now this we can do as well. For example, let's define a data type for natural numbers. And there are infinitely many natural numbers, so this is more interesting. This would look like this. So now, in this data declaration, what we do is the following. So, in this new example of nuts, what we do is we write data nuts. So nuts is a new type constructor. It has no variables after it, so it has arity 0. So in other words, this is the new data type that we define. And there are 2 data constructors. The first data constructor is called 0, and the second data constructor is called suc for the successor function. And now after every data constructor, we write the types of its arguments. So 0 gets no argument, therefore there is no type here. And suc should get an argument. So suc has an argument, namely an argument of type nuts, and therefore we write this. So in other words, this means suc is a unary function and it takes 1 argument of type nuts. So this is the argument type of the function suc. And the result, both of 0 and of suc, will be the new data type. So it will be this nuts. So in other words, if we write something like this, then we have introduced not only a new data type nuts, but we have also introduced 2 new functions, 0 and suc. And we have also given their type. So the type of 0 takes no input, and it gives you nuts as a result. So 0 is of type nuts. And suc is a function which takes 1 input. Input is of type nuts. And the result is, again, the new data type nuts. So if you look at the grammar again, obviously you can also have data constructors which take more than 1 argument. They can take many arguments. So if you define a new data type with this data type declaration, then the idea is, if you write this, then it means constructor 1 is a new function which takes n1 arguments. The first argument is of type 1,1, the second is of type 1,2, the last one is of type 1n1, and the result will be of this data type. So, in general, this would mean constructor I is a new data constructor which has the following type. It takes ni arguments. The first one is of type I1. The second one is of type I2. And the last one is of type INI. And the result is this new thing. The result is this new type that is defined over here. So the result will be the new type constructor applied to variable 1 until variable n. So this thing is a type, the new type that is being defined, and this data constructor, if we declare it like this, then we say this data constructor has this arity and the arguments should be of these particular types. So in the nuts example, if we write this, then it indeed means 0 is a unary, a function of arity 0, and this is a unary function. Now, how can you use something like this to represent interesting data structures like natural numbers? Well, the idea would be the following. So if we want to deal with natural numbers, we can use the following representation. To represent the number 0, we use the term 0. To represent the number 1, we use the term suc of 0, so the successor of 0. To represent the number 2, we use the term suc of 0, and so on. So in other words, the data objects of such a data structure are the terms that you can build with the data constructors. Now, the terms that you can build with 0 and suc are just these. 0, suc of 0, suc of 0, and so on. And so these are the data objects. And, well, if you say, well, these data objects, they look like natural numbers. Instead of suc 0, you could also think of 1. Instead of suc 0, you could also think of 2, and so on. So the data objects of such a new data structure are the terms built from the data constructors. So this is just a different way of representing natural numbers, but it does exactly the same. And you can now write algorithms on this data structure. For example, you can write a plus algorithm. So plus is now a function from nuts to nuts to nuts. So it wants to have two natural numbers from our new data structure and will give you back a natural number. So if the first argument is 0, then 0 plus y should be y. And if the first argument is built with the other data constructor, with suc, then, well, the first argument would have this form, successor of x. And how can we then compute the addition of successor of x and y? Well, we would call plus recursively, compute x plus y, and add 1 to the result. So this would be the successor of plus xy. And now this definition, this function definition, computes addition on our representation of natural numbers. And again, you can see these are patterns because they are just terms built from data constructors and variables. Here we have 0, here we have suc x. And in a similar way, we can define the half algorithm using our own data structure by using these patterns where we have 0, suc 0, and suc x. And again, this computes half just in the same way as we did it for the predefined integers before. Now, this shows how to define natural numbers ourselves. But of course, we can define lots of other data structures ourselves. For example, lists. If you don't like the predefined lists in Haskell, there is no need to use them. You can define them yourself. And how would that look like? Now, how would we define lists ourselves? Now, lists, let's call the new data type list. But list should be not a new type constructor of arity 0, but it should be a type constructor of arity 1. Because we want to have lists of elements of a certain type. So the idea would be to say something like this. So now list is a new type constructor of arity 1. And if we write list A, then the meaning is this represents the lists where all the elements have the type A. And A is a variable. So this represents the type of lists of elements of type A. Now, what do you think should be the data constructors? So we need functions with which we can represent every list. Right? So we need something for the empty list. We often call this nil. But the way how you call this is completely up to you. I mean, you just represent these data structures, and if you don't like the word nil, you can use null or empty or whatever. So this would stand for the empty list. What should be the type of nil or null? So what type should this have? It should be a list. It should be a list A, a list of objects of arbitrary type, because you don't know what type the object should have. So this should have type list A. In other words, if we declare this in this grammar, we should not add any objects here, because nil is a function of arity 0. It should not get any arguments. Okay, in this way we can represent the empty list, but in order to represent non-empty lists, what could we do? So we need something more. A way to insert an element, right? So how would we do? Let's say we call this function cons. So cons should be used to insert an element into a list. How many arguments should cons have? What type should cons have? It takes an A. If it just takes an A and returns a list of A, then it doesn't really insert an element into a list, because, well, assume you have a list, 1, 2, 3, you want to insert a 4. Well, if it's just A to list A, you cannot really take the original list into account. You just get, for example, a number, and now you have to return a list of numbers. So you need something more. List of A. So you have to take the element that you want to insert, you have to take the list that you want to insert it in, and the result will be, again, a list of A's. So how do we write this? Now, cons has 2 arguments. First an A, and then a list of A. The result will always be list A, because this is the data type that we just defined. But it has 2 arguments, namely A and list A, and Haskell syntax just requires to write these types of the arguments after the name of the data constructor. So we write A and list A. So by writing this declaration, we have introduced these 2 new data constructors. We have said that cons is a binary function where the first argument has type A, and then it waits for an argument of type list A. And that the result will be of type list A is clear because it's in this data declaration. So this is the way how to define lists yourself in Haskell. And this is completely the same as the predefined lists. The only difference is that we don't have this nice notation with these square brackets. But apart from that, this does exactly the same thing as predefined lists in Haskell. So if you dislike predefined lists, you can always use them. And now all algorithms that we had on lists, we can also define on our own data structure. So for example, the length algorithm is now an algorithm. We could now write an algorithm from list A to nuts. Both list A and nuts we define ourselves. So if you give it the empty list, it will return 0. If you give it a list which is not empty, then it is built with the data constructor cons. So it has the form cons x axis. And, well, then len calls itself recursively and increases the result by 1. And in the same way, you can also define append. And this works again in the same way, but now we use our own data type and our own data constructors, nil and cons. So, in fact, there's no need to use any predefined data type in Haskell. You can define all this stuff yourself. And of course, you can define lots of other things. So you can define trees and graphs and whatever. And you can also see these, whenever you want to have an infinite data type, so a data type which has infinitely many objects, you need recursion. And here we see recursion because this new type constructor list also appears on the right-hand side. In other words, one of the data constructors, namely cons, which is used to construct objects of type list, also takes an argument of type list. So whenever you have an argument of type list, you can make a new argument of type list using cons. That's the reason why we have infinitely many lists. And the same thing was true for nuts. Here, the data type that we just defined also appears on the right-hand side. So one of the data constructors, suc, also takes a nuts as an input. So whenever we have a nuts, we can make a new nuts by adding suc around it, which gives us infinitely many natural numbers. So in these declarations, recursion is allowed. and necessary in order to have infinite data structures. Okay, so this is how to introduce new data types into Haskell. Okay, now the last concept that I want to discuss when speaking about types in Haskell are so-called type classes. And type classes is a concept that you need in order to have ad hoc polymorphism in Haskell. Okay, so we have introduced types, and now in Haskell these types do not have to be completely separate from each other, but you can group some types together and say, well, these types all belong to the same class. So a type class is simply a set of types. So a type class contains many types. So there might be a type class which contains int and character and maybe our own data structure nuts. And there may be another type class which contains booleans and lists of characters and whatever. So a type class is simply a set of types. And the elements of this type class, so the types that are in this type class, are called instances of this class. So its elements, so the types that are in this class are called instances of the class. And the main reason why this is interesting is that in these instances, so in these types, you very often have the same functions. They look the same, but they do different things. So this is this idea of ad hoc polymorphism. You have one and the same function, but depending on the types of the arguments, it does different things. And these having a concept like this is called overloading. So for those of you who know Java, this might look a bit familiar. So typically, the instances, these instances have the same functions. So there are functions on all of these types, but with different implementations. So in other words, we have something like overloading. We have the same function names, but depending on the types, different things happen. And this is called ad hoc polymorphism. So depending on the form of the argument, of the type of the arguments, different things, we have different implementations. So let's look at an example. As you might know, Haskell has a predefined equality. So this is predefined, and this equality is also predefined. So what do you think is the type of these predefined operations? So equality takes two objects and checks whether they're equal or not, and then it returns true or false. And disequality, well, does the converse thing. What do you think is the type of this? A to B to bool. Okay, let me write it down. Now, if it would be like this, then you could write things like 1 equals true. That is something you're not allowed to write. So if you would write something like this would be an integer, this would be a boolean. If the type of equality would really be this, then it would be okay to write something like that, but that's not okay in Haskell. So Haskell requires that the objects on the two sides of the equality sign have the same type. So it is not, so this is not allowed in Haskell. And in order to require that the objects have the same type, it would have to be something like this. So then you would have to write A to bool. Now you could write 1 equals 1 and true equals true, and also 1 equals 2 or true equals false. But the problem is, of course, you want to have that this equality sign works between objects of different types. So it should work between integers, it should work between booleans, between characters, between lists of integers. But for example, what happens if you want to compare functions? So assume that we have two functions, square and double, and both would be of type int to int. And now, if this would be the type of equality, then you would be allowed to write something like this. If square equals double, then do whatever. Now, how should Haskell find this out? Whether these two functions are identical or not, Haskell would have to test them on all integers. There are infinitely many of them, so there is no way to check whether these functions are identical or not. So you are not allowed to write this in Haskell. In other words, you can use equality for objects, for arguments of different types, but not of any types. You can use integers, you can use booleans, but you cannot use functions. So in order to have this, up to now we cannot express this. But in order to express this, you can now add something here. So before this type, you can add a so-called context. And this context says, well, this type A may not be arbitrary, but it may only be a type from a certain type class. So as you remember, type classes are just sets or collections of types. And there is a type class ek for equality. And if we add this in front, so if we write this, then this means if A is a type which is a member of the type class equality, then for those types you can use these functions. So this is a function from A to bool, but not for arbitrary types A, but only for types which are member of the type class A. So this thing is not allowed because int to int is not a member of this type class. So in other words, now the type variable A may only be instantiated by types which are member of the type class EQ. So this type class EQ is predefined, but as you might imagine, you can define type classes yourself. And moreover, you can also, when you write a new data type, like nuts or list, you can also add it to existing type classes. So you can say, my new data type nuts should also be a member of the type class EQ. And if you say that, then you are allowed to write equality sign between the objects of your user-defined data structure. If you don't do this, then you're not allowed to write equality sign. So how do we do this? Well, obviously we have to extend our grammar. And, okay, this is a bit more than, so these are already a few extensions. So what we do is, there's now a new form of declarations which starts with the word class. So class introduces a new type class, and these type classes, by magic this thing moves. This is the name of the new type class. So it looks like a type constructor. It's again a string with a capital symbol, so that's a bit confusing. And this introduces a new type class. And what the meaning of this where is, we will see in a moment. So let's look at the definition of such a type class. How is, for example, this type class EQ defined? So this is predefined, and the definition could look like this. It's a bit more complicated in reality, but it could look like this. You would introduce a new type class by the word class. Then you would say how this type class is called. It should be called EQ. And, okay, now you have to add a variable, a type variable, and the meaning is the following. You introduce a new type class EQ, and you say, well, if A is a member of EQ, then this type A has certain functions. So for every type, certain functions must be present. These functions are also called methods, so you can see that this is heavily influenced by object-oriented languages. So you would now write the word where, and then after this word where, you can add declarations. And these declarations are declarations which are present for every type which is a member of this type class A. So for example, for every type in this type class, the functions equality and disequality are present. So here the functions equality and disequality are present. They would have indeed the type A to bool. Here these are just the A's which are in this type class. So for these A's, we are sure that they are in this type class EQ. And we can also say how these functions are implemented. So for example, we can say, well, disequality is simply implemented by not x equals y. But we give no implementation for equality. So this is very similar to the concept of classes and the class hierarchies that we have in object-oriented languages. So here we give, this is like an abstract class in Java. Here we give the type signature of some methods. So we say for every type A which is in the class EQ, there would be functions called equality and disequality. They would have this type. And we also might give some default implementations. So we might say, okay, disequality is implemented like this. How equality is implemented, we don't say. And then whenever we declare that a certain actual type is a member of this type class, we can give a concrete implementation of equality, and we can also override these default implementations. We can also say, well, in this particular data type, disequality is not implemented like this, but it's implemented in a different form. So these are default implementations. Default implementations for every type which is a member of EQ one has the functions equality and disequality, and in this type, for this type, we can implement these functions ourselves, and if we don't implement them, then this default implementation will be taken. There, these functions may be implemented, and of course, for every type, we can use a different implementation. So there, these functions may be implemented. And if they're not implemented, so otherwise, one uses the default implementation, which is given in this class.
One question on defaulting. When I use Hoc Polymorphism, does Haskell take, when I have a general function and specialized function, always specialized first?
What do you mean by general and specialized? This
maybe I've the append function. I've defined a append function for list of int and list of int to list of int.
Yeah.
Which may be very fast, and if the general function list A, list A, list A.
Also called append.
Yeah.
Okay. Now this you're not allowed to do. You may not simply on top level write two functions append, and one has type signature list of int to list of int to list of int, and one list of A's to list of A's to list of A's. So if you really want to do overwriting, you have to do it in a very restricted form. Now the problem is the following. In Java, you can do something like this. You can simply write functions with the same name but different argument types. You can just write them in any together on the same level, and then Java will decide which function to take depending on the types of the arguments. However, as soon as you combine this, and you have the problem that you have types and subtypes. So by having classes and subclasses, you have the concept that some types are subtypes of other types. But if you put this together with parametric polymorphism, so with these type variables, then if you don't take special care, then type checking becomes undecidable. That's something you never want. So type checking is done by the compiler. You want the compiler to determine whether your program is well typed or not, and you want him to determine this in finite time. So it's very difficult to combine these two forms of polymorphism into one language and still get a language where type checking is decidable. Now for Haskell, this is solved by limiting this form of ad hoc polymorphism. So this is a rather limited form where you can only have this overwriting for those functions which are declared in classes. So only here you can do something like overwriting. And this problem that you just described is excluded by the definition of the language. So you may not write something like that. In Java, they have also now introduced these two forms of polymorphism, and there they have solved this problem by making parametric polymorphism they restricted parametric polymorphism, and the subtleties of this are rather difficult. So really, so the form of parametric polymorphism in Java is much more difficult than the form here because there's some strange things happen, and they did that again in order to keep type checking decidable. So that's a bit of a problem. These two kinds of polymorphism don't work well together with each other. And to make them work, you have to do some restrictions. So let's see how we can do some overwriting. Now, in order to do overwriting, we need these instance declarations. Now, we had this class declaration. We have seen that here we introduce a new type class. This is a variable, which means that this stands for a type. And if this type is a member of this type class, then we have these declarations for this type. And for these declarations, the declarations, they look almost like ordinary declarations. You can have type declarations, you can have function declarations, you can have infix declarations, you can have pattern declarations, but only of a restricted form. So here the only patterns that are allowed are variables. In order to make it fast, whenever we do ad hoc polymorphism, this is resolved during runtime. So you don't want anything that takes a lot of time when you resolve these polymorphism problems, and therefore you have restricted forms for these declarations in the class, in the definitions of type classes. In the definitions of these instances, it's even more restricted. So here, in these instances, you can now say a certain type is a member of such a type class, and then you can override these declarations that were given in the type class, and you can add declarations also for functions which were not specified completely in the class. So let's do this. We have now this type class EQ, and let's now say that int is a member of this type class EQ. How would we do this? We would say int is a member or an instance of this type class. We would say, okay, this is the name of the type class, and int is a member of this. Now, if we just write this, then we have said, okay, int is a member of EQ. So after writing that, you are allowed to write the equality sign between two int objects. And if you do this, then, Haskell would look for the default implementations and execute them. Now, there is no default implementation for equality in this example, so it's a good idea to give a concrete implementation of equality. And to do this, we would write where, and now we can say how equality should be defined. Now, int is predefined. Int you can represent by usual integer numbers, like 1, -1, 2, -2. And so there's a primitive predefined function which is called prim_int, and this is a predefined function for equality on integers. So the reason for having this strange predefined function is that int is indeed predefined, and we present it in this way with usual digits, with usual numbers like -1 and 1 and 2 and -2. If you want to define your own data structure, like nuts, you can also say nuts should be an instance of this type class. Then you would say instance ec nuts where, and then you can define what equality means on your particular data structure. Before we do that, let's add the required rules to our grammar. So what you can do is, we've seen, you can declare type classes. You can say that certain types are instances of this type class, but these types that are also a bit restricted. So the only types that you can use here have this form. So it's a bit more restricted than arbitrary types. Namely, you can only apply type constructors to variables, not to more complicated types. So you can say that lists of A are a member of some type class. You may not say lists of lists of A. That is something you cannot say. So this is a bit restricted, again, to make it easier to resolve this ad hoc polymorphism during runtime. So now knowing that we have these type classes and how to say that a certain type is an instance of this type class, we can extend our grammar that we had before. So this looks complicated, but is not. There's not much change to what we had before. The only change is that now we can always add these contexts. So this is a context. In any type declaration, we can write contexts in front of the type declaration, and these contexts simply say that a certain type should be a member of a certain type class. So this whole thing, this thing with the double arrow, is called a context. So in general, contexts are written like this. The context says that variable 1, this type must be a member of type class 1, and variable n must be a member of type class n. And then whenever we have types, we can add this context. So when we have a type declaration where we say these variables have this type, we can add this context, and the context says that those type variables which occur here may not be instantiated by arbitrary types, but just by the types from the respective type classes as given in this context. And we can use these contexts also in the declarations of new data types, and also in the declarations of type classes and of instances. Now, what is this good for? Well, this is good for the following, for example. Imagine that we want to have another instance of our type class EQ. We want to say that lists can also be compared by equality. So we want to say lists are also a member of this type class, and we can then compare two lists and check whether the lists are equal. Now, obviously, not all lists can be compared for equality. Think of lists which contain functions. If we have lists which contain functions, then in order to find out whether two lists are equal, you would have to compare the elements. But if the elements are functions, functions are hard to compare for equality. So we don't want that all lists can be compared for equality. So we do not want to write something like instance of... So this is something we don't want to write, because if we write that, it would mean that all list types are member of EQ, but we don't know how to compare lists of functions. And in order to avoid this, we want to say, well, we only want to be able to compare those lists where we can compare the elements. I mean, in order to find out whether two lists are equal, we have to compare first element of the first list with the first element of the second list, and so on. So only those data types, list of A, should be in EQ, where A is already in EQ. So if A is a member of EQ, then lists of A should also be a member of EQ. And this, again, is a context. So this context restricts the type variables that we may use here. So for this A, we may only substitute types which are member of the type class EQ. This is the reason why contexts may be added to type class declarations. Now, how would we do this? Let's finish this example. Now, it would be nice to give an actual implementation of equality. For integers, equality is defined like this. For lists, equality should be defined in a different way. And now we can simply add function declarations like before. So, for example, we could say how equality is defined. So equality between empty lists should be true. And equality between lists that start with something which are not empty. Now, how will we find out whether these two lists are equal or not? we would want to check whether x is equal to y and whether x's is equal to y's. And these are two different equals. We want to check whether x is equal to y, and this is predefined and in Haskell, and whether x's is equal to y's. Now, these two equality signs look the same, but they are not. So this is equality on the data type A, and this is equality on the data type list of A. Because these are two elements of type A. These are two lists of type list of A. So this is a recursive call. Here we define equality for lists, and this is simply a recursive call. This, however, is something completely different. This is equality between elements of type A, and how this equality is defined depends on the type. So if we have lists of integers, then for this equality sign, we would use a different implementation, namely this implementation, if they are integers. So you can see that here we have this ad hoc polymorphism. This function looks the same. It's a double equality sign, but the implementation of the function differs. Depending on the types of the arguments, we take different implementations. Here we might take this prim_int implementation, and here we take, it's a recursive call, so the implementation is just the one that I gave up here. Okay, and the last call is missing, so otherwise the result should be false. So you can see, and the only reason that we might write this, I mean, x and y have type A, and writing an equality sign between two objects of type A is only allowed if A is a member of the type class Ek. And therefore we need this here. A must be a member of the type class Ek, otherwise we would not be allowed to write this. So that's the idea of type classes, and I will just discuss this a bit more in the lecture on Friday. Okay, see you then.